10 o'clock, so might as well get started. Thanks everybody for coming. Our first speaker this morning is Mikhail Khovanov from Columbia University, who will tell us how to categorify the ring of integers localized.
Thank you. I'd like to thank Newland Institute and the organizers for bringing us together. This is a joint work with Yin Tian, who is in the audience.
Mike.
Yeah, the microphone. Yes. So this was joined with Yin Tian, and we have a paper in the archive about this. And so the motivation here is that in the categorification to date, the integral structure was paramount. I mean, pretty much whenever we're categorifying something, it has to have an integral structure, be it link homology or representations of quantum groups. So quantum groups themselves, we needed to have everything defined over integers or over integers adjoint QQ inverse. And we just kind of have no idea what to do when things are not integral. And so in this work, we're trying to make a first step to deal with this issue, and which is one of the motivations. And it's also good to keep in mind that if you look at the hierarchy of very basic algebraic structures, natural numbers starting with 0, integers, maybe rational numbers, and so on, then we can think of the category of vector spaces as a categorification of the semi-ring of natural numbers. So we have here a categorification. The category of, let me put a technical condition that it's finite dimensional vector spaces. So if you have a vector, look at the category of vector spaces, it has operations, direct sum, and tensor product, which lift the addition and multiplication on natural numbers. What was, of course, much richer than n. So Z lifts to the category of complexes of vector spaces, up to chain homotopies. So this is over some field K. Here we can do it over some field K. There are some variations where you work with complexes of free abelian groups and so on. And if you take the Grothendieck semi-group, you recover n. If you take the Grothendieck group, K0, you recover Z. Grothendieck group is actually a ring because you have tensor product of complexes, complex M, tensor complex N gives you a complex M tensor N, and you can define multiplication. So using this tensor product, you can, when you descend to K0, you get multiplication, which is the usual multiplication in the ring Z. And of course, sort of passing from M to Z on this side requires working with complexes and forming cones. So lots of things that mathematicians do, they do over these base category of vector spaces and category of complexes. I mean, essentially, most of homological algebra have some kind of a base category of complexes in the background. In the very common case, it's a category of complexes of vector spaces. I mean, even when you work with some big category, like category of coherent sheaves, it's derived category. When you take homology, you land in a base category, typically of this form. So it's really kind of foundational for many things we do in modern mathematics. So you can kind of, at some point we wondered why there was nothing for bigger rings. I mean, not for kind of rings that come next when we learn mathematics in school. Like we encounter Q, we encounter R, and then maybe some of us encounter complex numbers and so on. But somehow category theory really stops here. I mean, you can do some variations. You can, I mean, if you kind of refine this category, add category of modules over, say, half algebra and so on, you can get something bigger than Z, but going in a different direction, not in the direction of Q. So the question is, can we get some interesting categories that whose Grothendieck ring is Q, maybe even R, but something along these lines where you can do division. So maybe one of the questions how to categorify division. And of course, what you want is a monoidal category. And we want to be able to take its Grothendieck group or ring. So we want it's most likely triangulated. And also, ideally, it should be Karoubi closed, so it should contain its idempotence. Karoubi closed to get something like Q or R. And we've tried to do it, and so far we've been able to come up with one example where we can prove that the Grothendieck ring is Zi joint 1/2. And we have conjectural examples where you put Zi joint 1 over n or or bigger rings that are subrings of Q. So I'll explain this, and sort of the most. The first thing to try is to just say, well, I want to let's just try to do the simplest case Zi joint 1/2. We want an object that corresponds to 1 to 1/2. So we want some object x, and the simplest thing to try is to say that x direct sum x must be isomorphic to the unit object, to the identity object 1. But this doesn't work for the reason that in a monoidal category or an additive monoidal category, endomorphisms of a unit object should be a commutative ring. Commutative ring, or if you just have a monoidal category, endomorphisms of 1 is a commutative monoid, because you can kind of move things around. There is a vectorial explanation for this fact. And if you have an additive category, endomorphisms of 1 is a commutative ring. Sometimes you can be kind of clever and you can generalize to supercommutative ring, but it's still in this neighborhood of being almost commutative. So the problem with this isomorphism is that if you have it, then endomorphisms, and you would want to have it because then on the Grothendieck ring, x is symbol of x is 1/2, because symbol of the unit object is the unit element of the Grothendieck ring of your category. So if you have a isomorphism, then if you look at the endomorphism ring of the unit object, it's the same as the matrix algebra of size q with coefficients in the endomorphisms of x. Just because you have this direct sum decomposition. 1 is x plus x. And of course, this is going to be some ring. But the problem is that the matrix algebra is very far from being commutative. And so that creates an immediate problem. So this way doesn't seem to work. So we were thinking what to do. And we look for a cheap way out of this issue. So we decided to just settle for to get a decomposition where x is isomorphic to x itself with a shift by an odd number, by 1 or minus 1. So we just chose -1. That doesn't really matter. Plus the identity. So in other words, we sort of rewriting this equation. We're saying, well, let's move x to the right. But moving x to the right requires us to work with complexes, requires us to work with triangulated categories. So we're going to say that x is shifted by an odd element, let's say -1, plus identity. Then in this isomorphism, this problem doesn't appear, but maybe something else does. So we need to unravel this isomorphism and see if it makes sense. So we're going to do that now. So that's the idea. So we're not looking for anything fancy, where we would try to build an exact triangle out of these 3 objects with shifts. We're just trying to stick to a direct sum decomposition. That's still the simplest possible thing to do, but with this caveat that one of the axes is on the other side. It has an odd shift. Okay, and we know that monoidal categories have a pictorial interpretation where we can have generating morphisms, for instance, of this type, going from an object x1 tensor x2 into object x3. So edges correspond to identity morphisms from some object xi to xi. If you put a blob from xi to xj. That's a particular generating morphism from xi to xj. You can do more complicated blocks with several edges going in, several edges going out, giving you generating morphisms between tensor products of generating objects, and then impose some relation. And that's one way to describe certain kinds of manual categories. Not all of them, but sometimes this is convenient. So we're gonna use this method to get a category for us, at least some initial category. So we want to have an isomorphism from x to the identity plus x with a shift by -1. The plus. So we need to have morphisms from x to 1 and from x to x with a shift, and morphisms back, which are mutual isomorphisms. So this map must be the inverse of this map. And we're going to use pictures to describe these morphisms. So let me use, so this picture, so we know that identity and the morphisms of identity, or so if we depict x by a dot on a line, we usually depict identity object by just empty line. Nothing goes here. And then, so we typically depict the generating morphism from x to the identity by just a line that ends in the middle with something here. Put some kind of label here to denote this morphism. So for our paper, we chose as a label a circle to denote a lollipop for a map going for the generating morphism from x to the identity. Back from identity to x, the picture should be going from nothing to a single point, x. So let me just draw a box here. And so for map from x to x, this map we chose a box notation, and we label this morphism x. Here we chose a circle notation. It's completely up to you. Just kind of try to make it consistent. Let me call it y, and let me call this z and z star. So these are the 4 pictures denoting these 4 generating morphisms. And then we can put them together next to each other. We can concatenate them in various ways to get a manual category. So let us write down the relations. So the relations say, for instance, that if you go from x to x this way plus this way, this must be the identity map. So that relation tells us that the sum of these 2 morphisms is the identity. So this is x, y, this is z star. So in other words, going from x to itself this way plus going from x to itself this way, that's the second picture. So we go through unit elements, so there's nothing here. This is the identity. And there are more relations. Going from 1 to x and back must be identity. So this is just the empty picture. And this was the empty picture. You can erase it. And the value of this picture is 1. This is identity. This is also identity morphism of a unit object. So this is z star. And let me write everything else. So this is 0. Okay, this saying that if you go from x to this x, and then back here, that's identity, because you're projecting onto the wrong direct summand. You're putting x inside this as direct summand and projecting onto the complement. So that product is 0, and the other relations are this. This is 0. That's going from here to x and then projecting onto the other piece. So that's 0, and also one more relation, I think, is this is the identity. So going from this x to this x and back is the identity. So this is x. Notice that the order is reversed. Here x is at the top, here y is at the top. So this way is identity, this way is not. So in particular, you can see that y is the inverse of x on one side, but not on the other side. So you see you have a one-sided inverse in this picture. All right. So now, what can we do with these relations? We can just generate a monoidal category. category. Actually, let me call it something. Let me call it C with objects x tensor n, where n is greater than or equal to 0, and these generating morphisms and relations. And so maybe at first we're gonna make the category triangulated later. For technical purposes, for now, you can just think of this as maybe just x, but this morphism has a homological degree that we'll remember later. So there are some homological degrees of x, y, z, and z star. The degrees are 1, -1, 0, and 0. And this, in terms of pictures and relations, this means that, for instance, because x and y have odd homological degrees, when we draw them on the plane in the picture, when we change the height of x relative to y or x relative to x, we're going to have a minus sign come out. So because we want to have everything super commutative, since we're going to live eventually in the digi world, we need to impose super commutativity, which in practice means, for instance, that if you have an x, when something happens, a y is minus x going first and y happening later. So height changes will have minus signs coming out of this rules for x or y, or if you have two copies of x, changing the height is a minus sign as well. But no signs when one of the two terms is a z or a z dual. So there is a minus sign here. Okay. So first of all, we need some non-degeneracy result saying, well, let's look at these relations and take a picture of a morphism between tens of powers of x and simplify it as much as possible. So I want to say that, just simplify in a natural way using these relations, and when we cannot simplify further, that should be a basis element. So there is a kind of first step, describe Hom spaces between x tensor n and x tensor m. And so if you look at what can happen, well, if you have, for instance, in some way, this category is not going to be particularly complicated, because notice that all the pictures, they have this very local flavor. We never see pictures that would force us to create planar networks. So we never have pictures where we have three edges together at one vertex, three or more edges together. It's always at most two edges. So you can think of it just a single line with some blob on it. Or we can have a line starting or a line ending and nothing else. It turns out that because of this, you can reduce any element that we can build out of these pictures to a linear combination of fairly simple elements. And in these elements, we're going to have some number of lines that go through and carry stuff on them, some number of lines that float to the top and have maybe some stuff on them, and some number of lines at the bottom. So we call this kind of short lines, and these are long lines. And this is kind of the simplest possible situation, because you don't have to deal with networks and complicated planar global diagrams. And I want to say that so there is a kind of similar example, but for different algebras that you can find in a joint work with Radmila from several years ago. But so let's think some more about this. So what can we reduce? So first of all, so we can reduce anything that's floating, anything that goes from identity to identity. We can reduce it to a number, because this is a 1. We can always move. Let's see, if you have a box below a circle, we can just cancel this. If you have on a line, if you have a box above a circle, we can simplify to something to a linear combination of two more elementary things, to just vertical line with few decorations, or something which has a gap in between. So that's a simplification. So because of this, at most you can get is for lines that end at the top, you can have a box here and then some number of intermediate boxes. So you will not get circles, because circles will give you 0. So circles at the top line, so kind of, well, either you can cancel with something in the middle, or if you push the circle all the way to the end of the line, it's going to be 0. And likewise, you cannot have, if you have a box on a line at the bottom, this box will either cancel with another circle on this line, or it will float to the top of the line where it's going to make it 0. So here you can just have some number of boxes. At the bottom lines, you can just have some number of circles terminating in this circle. So there are kind of two types of circles, this circle and this circle, denoting the end of the line. And then in the, so maybe I just call this n, meaning we have n circles here. And I can call this n, meaning we have n circles here. And for lines that go through, well, if you have both circles and boxes on them, we can always reduce to something simpler. So we can either have some number of circles or some number of boxes or nothing. So for lines that go through, you'll either have some number of circles, n, or some number of boxes, n, or it just goes through. That's it. And so notice that if we actually kill this term, then the box and the circle, they become two-sided inverses. And if you kill this, we get a two-sided inverse. So you should think of this in a certain quotient. This is inverse to this. So a little bit like Laurent polynomials in a single box or in a single circle, but modular simpler stuff. And so the theorem so in particular, so there is a theorem saying that this describes, I'm not being very precise here, it describes a basis of Holmes from x tensor n to x tensor m. And this means that the basis of Holmes in this category will be given by diagrams where we have some number of through strands or long strands with a decoration on each of them of one of these three types of positive n. And then you have some number of short arcs at the bottom and some number of short arcs at the top, with again decorations being boxes. So this could be some number and 1 and 2 and 3 and so on, boxes. And because of the possible minus signs, you need to pick an order every time you choose a diagram, which is again not an issue. But kind of the first step is to make sure that what we have is not just a spanning set, but a basis. And this is fairly straightforward, and you can generalize. And what you really need is you can generalize to the case where you have an algebra describing endomorphisms of x. I mean, what we're kind of starting with is an algebra that should describe endomorphisms of the identity object plus generating object x. And so in this picture, in this picture we have 4 such generating morphisms. Subject to certain relations, and in the relations we have at most, in every term in the relation we have at most one strand. Sometimes it kind of there is a gap in the middle, so we go to no strands. But so if you want, you can axiomatize with it. You can describe a situation when this is some algebra, maybe algebra R. You have an idempotent E of projection onto the unit element, and then you can write down some simple conditions to be able to easily get a monoidal category out of this, where R describes the morphisms of the sum of x plus 1, and the idempotent is projection onto the unit object. So there are some kind of simple axioms that will lead to a similar picture where you have some stuff, short arcs with some stuff on them, top arcs with some possible, they could carry some summons of this ring, and also through lines which carry again some piece of this R with some easy to write down relations. And then this is a particular case. But again, this is a very special case because ignoring this shaped by 1, x is isomorphic to 1 plus x. There is some kind of this infinite iteration built in. X is 1 plus x, so it's also 2 plus x, 3 plus x, and so on and so forth. Okay. So we have a basis for this category. And so also if you, in our situation, endomorphisms of x plus 1 are also isomorphic to endomorphisms of x, just because we set things up this way. And we can recognize so endomorphisms of x would be pictures which start and end with a single dot, and some stuff happens in between. And we can actually recognize this endomorphisms of x because we have x and y. We can also create some gaps here, but this is a linear combination of xy minus this is xy minus identity. So we can actually get this out of x and y. So what you'll get is that in our situation, the morphisms of x is going to be the algebra over a field K with generators x and y, and the relation yx is equal to 1. Is equal to 1. But not the other way. Not the other way. So let me call this algebra something. Maybe let me call this algebra A1. So then if you look at the product in the other direction, xy is an idempotent, but it's not a unit element. And if you look at 1 minus xy, so 1 minus xy is equal to this picture. And then if you use this picture, you can stack boxes on the top, and you can stack circles at the bottom. In other words, you can take this 1 minus xy, multiply by x to the n, y to the m, and you do this over all n and m. So you get an ideal. Let me actually look at the span of this. Span of this, maybe k. Span of this set. We get an ideal J, two-sided ideal in A1. Ideal J. And the quotient is just polynomials, Laurent polynomials in X. Because in the quotient, X and Y are two-sided inverses. So the quotient is just Laurent polynomials. Well, what is the ideal J? Ideal J, well, it has the generator 1 minus xy, and you can add boxes, you can add circles. J ends up being just the matrix, direct limit of matrix algebras. It's matrices of size n with coefficients in k, with matrix element E and M being just n boxes here and m circles here. So in other words, this maybe it's a little bit funny because this A1 is finitely generated, but inside it has this ideal that is a matrix algebra that is a direct limit of finite matrix algebras. So it just gets bigger and bigger. So this is not finitely generated, but it's this direct limit. So this is A1, so it's in the morphisms of X. In this category, we forming tells the powers of X, and naturally things get more complicated. But whenever we look at endomorphisms, for instance, of X to the n, you'll have a filtration by looking at how many strands go through. Because strands, if you fix the number of strands that go through, then we can get a two-sided ideal by looking at all of these diagrams with at most k strands going through, and the rest of strands just getting lost or terminating above or below the middle line. And this is known as the Jacobson algebra, and it goes back to around 1960, because this is roughly when he introduced it. So how do we get, so we still need to introduce a triangular structure on this category. So far we have the tensor powers of x and halves between them. So to get the tensor structure, so let me, guess I need to erase something. So we should start with this kind of category C with objects tensor powers of x. And we want to build a triangular category out of this. So the standard way to do it is to pass to some pre-triangulated envelope of this category where we add shifts. We add shifts, finding direct sums, and cones in an iterative way. So just keep doing it. So then we want to pass to then we want to restrict to morphisms which have degree 0, homological degree 0, and pass to homotopic category. So we pass to the homotopic category of this category. And then we form the Karoubi envelope to get, let me call it homotopic category tilde of C pre-triangulated. And this is actually good enough, and turns out to be equivalent to the subcategory of compact objects in the bounded in the derived category of compact objects. Objects in derived category of C. So another way to think of it is that if you look at objects x to the n, overall n, and morphisms between them, so you get some category. Think of it as a DG category with a differential D, but D is 0 on yeah, notice again that we wanted to have a shift in the homological degree, and we needed to set up an isomorphism from x to 1 plus x shifted by minus 1. So for instance, morphisms x and y have non-trivial homological degree. So at some point we need to work with complexes, but we also should think about direct harms, so harms from x tensor m, overall n m greater or equal to 0. So think of this as a DG algebra with trivial differential. So we never needed to introduce, to have differential act non-trivially in this construction. Differential will appear once you pass to this category, because in this category, you need to build cones of morphisms, direct sums, etc. So very quickly you'll have non-trivial differentials in this category. But in the C itself, you don't have a differential. It's equal to 0. Equal to 0 on all of these harms. And you can think of this as it's kind of an algebra. If you have n and m go only up to some number n, that's actually a unital algebra with trivial differential. So if instead of the sum you put m from 0 to n, you get a unital DG algebra with trivial differential. If you send n to infinity, well, the only minor modification is that it's not unital. But otherwise, everything else is as before, so you can form the corresponding categories of complexes. Again, this is very similar to starting with category of free modules and then building up complexes of free modules, adding projectors so that you're working with complexes of projective modules and so on and so forth. So this is kind of slightly fancified version of how we pass from the category of modules to the category of complexes of projective modules up up to chain homotopes with some finiteness condition. And so same here. So the DG algebra has trivial differential, but once we pass to complexes, we will have non-trivial differential inside those complexes. And for if we limit our indices up to some n, that's an actual unital algebra, and otherwise it's a direct limit, and which is familiar to us because that's how we work with modules over quivers with infinitely many vertices. You just take direct limit of those representations. Of course, I mean, once we pass to this derived category, of course, we cannot always use these pictures to describe objects, because now objects are built out of x to the n, and idempotents inside these things we build out of x to the n in some complicated way. So the pictorial description is best for the starting category C. Well, this has tons of objects that we don't expect to have a similar easy understanding using diagrammatics. So what we want to do is to kind of, so we want to get a category with a Grothendieck group Z adjoint 1/2. So what we, so this category is triangulated. It's also monoidal. It's monoidal because category C is monoidal. You can just put these pictures next to each other. And then if you build one complex out of this object, another complex out of this object, you can put them next to each other, and that's your tensor product. So this category is definitely monoidal as well. It's also Cherebi closed. If you take, so let me call this category something, maybe D. So we can look at K null of D. So it's a ring, and we can map the ring Z adjoint 1/2 into this K null of D by taking, well, of course, the symbol of the, well, of course, 1 goes to the kind of symbol of the unit object, but 1/2 goes to the symbol of x, and we can do it because of this relation. And here we're using square brackets in two possible ways. This is to denote the image of an object in the Grothendieck group or Grothendieck ring, and this is to denote the shift. So like two different uses of square brackets, but this is well defined because of this relation. So if you take this relation, pass to the Grothendieck ring, you get that you get the condition that 2x is the symbol of the unit object. So it's okay to send 1/2 to x, and we get a ring homomorphism. So the problem is that we don't know whether it's injective and whether it's surjective. So let me call this gamma. So the theorem that we prove, the main theorem that we prove in this paper is that gamma is an isomorphism. And under the condition, if the characteristic of the ground field is 2, and so we feel that this is actually true for all fields K, but so far we are able to prove it for characteristic K equal to 2. So so what is the difficulty in establishing this result? Well, notice that here we're taking direct limit of this. I mean, if we fix n, we have a unital algebra, but we really need to iterate and pass to the direct limit. But it's well known that K null commutes with direct limits, so you really just need to understand the K null of this algebra, of the DG algebra, when you limit n and m to go from 0 to some number n. So that's enough. Another thing is that if you take this isomorphism and if you tensor it with x tensor n minus 1, you're going to get the formula that x tensor n is isomorphic to x tensor n minus 1 plus x tensor n with a shift by minus 1. So you just tensor with x to the n minus 1. And what it tells you is that the x n minus 1 is a direct summand of x to the n. So here you're looking at endomorphisms. I'm going to expand this. So this is endomorphisms of 1 plus x plus etc. plus x to the n. But actually, x, all the lower x's, they are summands of this bigger x. So just like Merita equivalence, you already have xn minus 1, xn minus 2 sitting inside x to the n as direct summands. So you can remove them at the cost of not doing anything to the Grothendieck group. So you can look at from the viewpoint of computing K group, it's the same as to look at the K group of endomorphisms of x to the n, because these are already summands of x to the n. Here, x minus 1 is a summand, and you can iterate and get x minus 2 as a summand, and so on and so forth. So I can reduce to computing to understanding this. Now this is a DG algebra. It just means you have pictures from n points to n points with all these relations. It's a unital DG algebra. It has the ideals inside where you restrict the number of through strands to some number k less than or equal to n, and we are able to compute k-null group of this algebra. Using using some manipulations and using the fact that it has a suitable ideal where some strands become short, don't go through. And it still turned out to be quite hard at least. I felt it was hard, maybe Ian felt it was easier. I don't know, but so the difficulty here, first of all, is computing K groups for DG algebras is not well developed. And these DG algebras are particularly awkward because they have non-trivial elements in all degrees, in both positive degrees and negative degrees. And so this is just an awkward situation, and not much is known about computing K groups of DG algebras in general, and just not many examples. So we were able to forage through the literature and put together enough known results and sort of our computations to get to the answer. And the answer was that K-null of the endomorphism.
Michael, you keep emphasizing that, as a DG algebra, this thing's very hard. But I thought the differential is trivial even on x tensor n, right?
Yeah. So it's a formal DG algebra. So the differential is 0 on the algebra. But once you look at, of course, when you look at the category of DG modules, the differential is not 0. And so it's a very complicated category. And in general, people just don't have good tools for computing K groups of DG algebras.
So it's not K0 of this algebra, it's K0 of that category of DG modules.
Exactly. So what we want is to compute K-null of this DG category. And K-null of this DG category ends up being direct limit of K-null of the DG algebra of endomorphisms of x tensor n as n goes to infinity. And you can check that under the inclusion that as you go from n to n plus 1, if you look at K-nulls, you get z going to z multiplication by 2. So you can check that K-null of this DG algebra is z, which is quite a non-trivial result. We felt, and then you check that this inclusion induces multiplication by 2 map from K-nulls, and then you get K-null as a direct limit of these copies of z under multiplication by 2. This z for each endomorphism of x to the n. And because of this K-null is the direct limit of z's under z goes to z multiplication by 2. And of course, once you fix and you don't have monoidal structure, to have monoidal structure, you need to take all n together. So each of these individual categories, DG categories, is not monoidal, but the direct limit is. So when we're computing the K group, we're computing just the group of this one, which ends up being z, but it does have a ring structure. But the direct limit does have a ring structure, and because it's this one, it's necessarily z adjoint 1/2. Okay, so we get the answer. We get the answer, and so we get this kind of one example. And again, somewhere we need characteristic k equal to 2. In one of the computations, for instance, for k1s, and we're computing k1 of certain of a DG ring where you ignore the short arcs, just you have the long arcs. We kind of the way we compute it needs this property, but it's probably we don't think it's essential, but this makes our life easier. So we get this. I mean, so conjecturally you can just put some axes on this side, some axes with shift on this side, and hopefully that gives you clarification of zi joint 1 over n for any n. But it's a conjecture, and things become hard once you have more than one x on each side. Things become hard because you'll have many more morphisms to deal with. So here we had rather few morphisms between x and x and x and 1, but once you add x's, when you start accumulating x's on various sides, you'll get lots and lots of morphisms between these copies of x's. And then as a result, the endomorphism ring of x, from that endomorphism ring of x, ends up having exponential growth. As an example, for instance, a free ring on some number of variables has exponential growth. So these are kind of not free rings, but close to free, and it's exponential growth. So we just kind of, and they're hard to deal with. It's hard to, you can still draw these pictures, but then it's hard to get a handle on the Grothendieck groups of the corresponding DG categories. And it also turns out that this kind of isomorphisms have been considered in the non-DG case under the name of vivid algebras or vivid path algebras. People would consider the situation where, for instance, you will look for a ring R such that it's isomorphic, such that the free module over R is isomorphic to a sum of n copies of itself. Because for these rings, the notion of rank of a free module is not well defined. If you have the free module is a morphic sum of several copies of it. We can produce an universal ring of this form because you'll just need an isomorphism from here to n copies of R and back. So you'll need to have two n elements of the ring, n elements going this way, and elements going that way, subject to some quadratic relations. You can write them down. You get what's called vivid algebras. In this algebras, the free module has the property that x is isomorphic to x, to n copies of x. And when people generalize, where they would have not a single module, not a single free or projective module, but several of them, and the relations would generalize linear relations. So you could have, for instance, I don't know, let's say, lifting the equation x plus y equal to 2y plus 3x to a relation where you have x direct sum y is isomorphic to 2 copies of y plus 3 copies of x. And you can have more than one such relation. So people have looked at this vivid path algebras. I studied them. There is kind of a survey. They're quite popular and useful in operator, in ring theory. But the catch is that almost immediately you get into algebras of exponential size. And also people weren't interested in taking monoidal envelopes like we do here, because we start with these homes between x and 1 and back, and then 4 monoidal envelopes. So people just studied rings where you have these isomorphisms with the projective objects over your ring that together generate the ring. So they would categorify systems of linear equations of the form vector x equals to ax for some matrix A with non-negative integer coefficients, or they would look at rings that categorify homogeneous linear equations of the form ax is bx, where matrices A and B have non-negative integer coefficients. So this is a sort of a popular topic on the intersection of ring theory and operator theory, which goes under this name. But you can also look at take the rings and form a sort of monoidal closures of those rings. You can, for instance, look at the, say, I want object x. which is isomorphic to identity plus 3 copies of x. So if you want such isomorphism, you can draw similar diagrams, get similar generators and relations. Notice that in the Grothendieck ring, if you pass to the corresponding category, the symbol of x should correspond to -1/2. Because you can cancel 2 x's and then get symbol on the Grothendieck ring level, you get symbol of x is equal to -1/2. And then sort of conjecturally, that's another way to get Grothendieck rings that are z adjoint 1/2 in this example, or z adjoint 1/n. Just keep adding x's here to get z adjoint 1/n. But that's a conjecture, because to prove this conjecture, we would need to know some facts about k groups of tensor powers of the sleeved algebras. Because essentially, roughly speaking, you have a copy of such algebra on every strand. And then you need to know k group of something of this form, which modulo the ideal of strands that end short is tensor power of an algebra of this form. And actually, we found a paper where people kind of discuss k-null, and they don't know how to compute k-null. Kind of at the limit of current knowledge in these algebras. But this, if you do this direction, you can avoid, for a while, you can avoid doing homological algebra, because you don't need DG, you don't need complexes. You can just build a monoidal category out of tensor powers of x. Monoidal additive category, take its Grothendieck ring. It's conjecturally this, or you can do some variations. But the difficulty is that you have to work with algebras of exponential growth. So it's a kind of a trade-off. You either do homological algebra, or you have to deal with algebras of exponential growth. I don't know if there's some kind of deep analogy here. I'm not sure. But sort of, again, the motivation is we're kind of trying to do codification in the non-integral case. And we bump into this complicated structures in either case. One kind of another positive sign is that it's possible to do a variation of this isomorphism sticking to just 2 copies of x. Whenever you have more than 2 copies of x, you force into exponential growth. But you can do a variation of this with just 2 copies of x to conjecturally categorify z adjoint 1/p and the p root of unity e to pi I over p using a combination of pdg with this kind of isomorphism. So that's additional positive in the story. But we kind of, and again, the goal is to get base categories over which you can do codification not over z, but over z adjoint 1/n, q, and similar rings. But this is just the first step. And the only result we have is this result. We hope that this can be dropped. And so there are various connections. On this side, the connections, for instance, you can connect to Thompson groups of homeomorphisms of the Cantor set, because here you're saying that R is isomorphic to n copies of R. So it's just like Cantor set isomorphic to n copies of, homeomorphic to n copies of itself. So this is a linear version of the Cantor set, if you want. But we just have sort of one such example, and there's kind of main questions whether what are other examples, and what are the examples where you can build, which can be used as base categories to build some version of homological algebra, but not over Z, not over complexes, but in some other, over more sophisticated base rings. And of course, almost nothing is known. So let me stop here. Thank you.
Any questions?
Easy to explain my unique characteristic to the proof.
Oh, yeah. So for characteristic, I think the excuse me. We don't think it's essential, but I think we're running long, yes. So we need to, somewhere we compute k-null, we want to compute k-null of this endomorphism ring by induction on n. And somewhere we want to say that in the sequence of k-null groups for endomorphism of 10 to the power of x, somewhere we need to deal with k1 of the ring, which is the quotient of this endomorphism ring by the strands, by diagrams that don't make it through. So, and the quotient is just, it's algebra of n strands, where here you have just circles or squares, because so it's k1 of the algebra, which is k of x1, x2, xn plus minus 1 that anti-commute, and they have non-trivial homological degree. So homological degree of x1, xn is 1 for each. And we want to say that k1 is, we want to say that it contributes kind of nothing to k-null. So we want to say that it's torsion. And we kind of end up, it's easy to use one of the definition of k1 of a DG category to conclude with its torsion in this particular case, in characteristic 2. But the catch is that it's just even definition of k groups for DG categories excuse me, is complicated because you need to deal with Quillen's original exact category setup. So ultimately, you kind of have to unravel to homotopic groups. You can avoid unraveling all the way using other people's work, but the issue here is that we don't have a well-developed theory of computing high k groups or even k-null for DG algebras. So computations are difficult. But in characteristic 2 case, we were kind of, it was easy to see that k1 contributes nothing to our computation because of using one of the definitions of k1 of DG categories. Yeah.
If I have any like triangulated monoidal category or something, I can look at an object which is like identity plus identity with the shift by 1 minus 1 plus identity with the shift by minus 2 and so on.
Yeah. Okay.
Does this give me a sort of categorical algebra? Or
But this object is not compact. I mean, it's a bad object.
yeah, I agree. Okay.
No, but then if you allow those objects, k-null is going to be 0. If you allow infinite direct sums, because here things are not infinite. You can split off. Here x is 1 plus x with a shift, but you don't get an infinite sum. It's always a finite sum. You can get arbitrarily long sum, but it's always finite. So if you allow infinite direct sums, most certainly your k-null is going to be 0 no matter what you do.
You need the characteristic 2 assumption for surjectivity and injectivity.
Sorry?
Can you prove it's like either surjective or injective?
No, I'm pretty sure. I think it should be it's an isomorphism for any characteristic. It's just maybe it's a matter of maybe just getting more comfortable with k groups of DG categories. It doesn't feel kind of essential.
When you prove one of the two, what's the
Is one of the directions obvious? I don't know. Can we show surjectivity? Yeah, we have to look at the proof again.
All right, so there's no other questions now. You can ask them later. Thank Michael again. We'll have a break now until 11:30.